What lies beyond everything we know? Is it simply more space? More galaxies? Or something far stranger, something that bends the very nature of our understanding? When we stare into the night sky, we are not just looking at distant stars, but peering into the ancient past of a universe, still expanding, still unfolding its mysteries. The further we look, the older the light, the deeper the question. What comes after all of this? What lies beyond the edge, beyond the stars, beyond the veil of what is observable? Our solar system, nestled within a quiet arm of the Milky Way galaxy, is a speck of dust in a galactic ocean teeming with hundreds of billions of stars, and the Milky Way itself is just one of perhaps 2 trillion galaxies scattered across the observable universe. But even as we map and model the known, there remains a vast, dark frontier and outer realm that no telescope can touch and no spacecraft can ever reach. A place beyond the reach of light itself, a region where the fabric of space-time stretches faster than light can travel. This edge is not a wall, but a horizon, shaped by the expansion of space, driven by an unseen force, dark energy. As space expands, galaxies beyond a certain point recede from us faster than light, not because they move through space quickly, but because space itself is stretching, pulling everything apart. This means that there are parts of the universe we will never observe, no matter how long we wait. And beyond that, there may be even more an infinite landscape of cosmic variation where the laws of physics differ, where time flows in reverse, or where matter never formed. This is not science fiction. It is a genuine scientific possibility born from models like eternal inflation and the multiverse theory, which suggests that our universe could be just one bubble in a vast multiversal foam, each bubble a different universe with its own set of physical constants, dimensions, and perhaps even intelligent life. These ideas are born not from imagination alone, but from the mathematics of cosmology, from the limits of general relativity and quantum mechanics, from the subtle signals of the cosmic microwave background, and from patterns in the distribution of galaxies that whisper secrets about the earliest moments after the Big Bang. And yet, even as our theories grow more bold and our instruments more powerful, we are still confined to one vantage point, one tiny corner of a possibly infinite reality. The space between galaxies is not empty, but filled with invisible matter, radiation, and the ghosts of dead stars. The space beyond the universe may not be space at all, but an abstract realm of potential, waiting to be mathematically modeled, philosophically pondered, or spiritually interpreted. It is a place where science and mystery dance side by side, where questions outnumber answers, and where every discovery opens 1,000 new paths of inquiry. The universe is not a static dome, but a living, breathing entity, one that evolves, stretches, and births new possibilities across scales that dwarf comprehension. As the James Webb Space Telescope peers deeper into the past than ever before, capturing light from galaxies formed just a few 100 million years after the Big Bang, it challenges us to redefine what we know and, more importantly, what we don't. These deep field images reveal a cosmos teeming with unexpected structure, surprising order, and hints of something more, something lurking just beyond resolution, just beyond reach. And perhaps that is the true nature of what lies beyond. Not a final answer, not an end, but a mirror of our own desire to understand, to explore, to push past limits we once thought unbreakable. Maybe the emptiness we imagine beyond the stars is not truly empty, but simply unfamiliar, filled with rules and realities that make no sense to us yet. To contemplate the beyond is to confront the fragile boundaries of human knowledge, to accept that our greatest tool, science, mathematics, philosophy, still young, still evolving, still learning to ask the right questions. What lies beyond the universe may remain forever out of reach, or one day be as real to us as planets once hidden by distance and darkness. It may be a higher dimension folded into the very fabric of our space-time, a place where time loops or splits, where gravity plays by alien rules, or it could be nothing at all, a conceptual limit rather than a physical one. And if that's true, then maybe the quest to understand what lies beyond is not about finding a destination, but about transforming the traveler. For as long as humans have existed, we've looked upward and outward, From cave paintings of stars to the latest quantum theories, not because we expect easy answers, but because the very act of asking defines who we are. To wonder what lies beyond is to admit the limits of our vision while daring to stretch it anyway. It is to recognize that knowledge is a horizon always just out of reach, forever expanding, like the universe itself. And so we keep looking, not for certainty, but for meaning, for connection, for the next clue in the grand cosmic puzzle that tells us not just what is out there, but who we are in here. For most of human history, the universe was thought to be small, ordered, and centered around Earth. Early civilizations looked up at the night sky and saw divine patterns, mythological stories, and celestial cycles that guided their agriculture, navigation, and rituals. The Babylonians tracked planetary movements. The ancient Egyptians aligned their pyramids with the stars, and the Mayans built intricate calendars based on solar and lunar cycles. However, it was the Greeks who first began formalizing a scientific view of the cosmos. Around 2,500 years ago, philosophers like Anaximander proposed that Earth floated freely in space, while Pythagoras suggested that the universe could be understood through mathematics. The model of concentric celestial spheres, later expanded by Aristotle and Ptolemy, placed Earth at the center of the universe, surrounded by crystalline orbs that carried the moon, Sunday, and planets. This geocentric model reigned for over 1,000 years, cemented by religious doctrine and the apparent motion of the heavens. Everything began to shift during the scientific revolution. In the 16th century, Nicolaus Copernicus published his heliocentric theory, placing the Sunday at the center of the solar system. Though initially controversial and resisted by many institutions, this idea triggered a profound transformation in our understanding of the cosmos. Galileo Galilei's use of the telescope in the early 17th century provided crucial evidence supporting heliocentrism. He observed moons orbiting Jupiter, the phases of Venus, and mountains on the moon, all of which contradicted the idea of perfect heavenly spheres. Johannes Kepler further refined the model by describing planetary orbits as ellipses rather than circles, introducing the first truly mathematical laws of planetary motion. Isaac Newton's publication of the Principia Mathematica in 1687 offered a universal theory of gravitation, unifying the motion of celestial and terrestrial bodies under the same physical laws. With Newton, the universe became a mechanical system governed by predictable forces, an idea that would dominate scientific thinking for centuries. By the 19th century, astronomers were measuring the distances to stars using parallax, analyzing starlight through spectroscopy, and beginning to grasp the scale of the Milky Way galaxy. In 1915, Albert Einstein introduced his general theory of relativity, revolutionizing cosmology by showing that gravity was not a force transmitted through space, but a curvature of space-time itself. This opened the door to a new way of understanding the universe as dynamic and malleable. Just a few years later, Edwin Hubble discovered that distant galaxies were moving away from us, revealing that the universe was expanding. This observation, combined with Einstein's equations, led to the development of the Big Bang Theory, the idea that the universe had a beginning, a hot, dense state from which it has been expanding for roughly 13.8 billion years. The 20th century brought rapid advancements in both observational and theoretical cosmology. The discovery of the cosmic microwave background radiation in 1965 by Arno Penzias and Robert Wilson provided compelling evidence for the Big Bang, revealing the afterglow of the universe's birth. Further refinements in observational technology allowed astronomers to peer deeper into space and further back in time. The launch of the Hubble Space Telescope in 1990 transformed our view of the cosmos, producing iconic deep-field images that revealed thousands of galaxies in what seemed like empty patches of sky. These images helped solidify the idea that the universe was not only vast, but filled with structure on every scale, from stars to galaxies to clusters and superclusters, interconnected in a cosmic web. Milestones in space exploration also paralleled these theoretical leaps. The launch of Sputnik in 1957 marked the beginning of the space age, quickly followed by human missions like Yuri Gagarin's first orbital flight and the Apollo moon landings. These ventures extended humanity's reach beyond Earth and symbolized our desire to explore not just the known, but the unknown. Robotic missions have since visited every planet in our solar system, and probes like Voyager 1 and 2 continue to send data from the interstellar boundary. These missions have expanded our understanding of planetary systems, cometary behavior, and even the outer edges of the Sun's influence, the heliopause. One of the most important concepts to arise from these developments is the notion of the observable universe. The observable universe refers to the region of space from which light has had time to reach us since the beginning of the cosmic expansion. Because the universe is only 13.8 billion years old, and the speed of light is finite, we can only see a limited sphere around us. However, due to the expansion of space itself, this sphere stretches much farther than 13.8 billion light-years closer to 46.5 billion light-years in every direction, forming a diameter of 93 billion light-years. Beyond this horizon lies the unobservable universe, regions so distant that their light has not yet, and may never, reach us. The concept of the observable universe is not just a technical boundary, but a profound reminder of our limitations. It challenges the idea that we can know everything and underscores the role of perspective in cosmology. It also raises fundamental questions. Is the universe infinite? What lies beyond what we can observe? Could there be other regions with different physical laws, different particle configurations, or even different histories of cosmic evolution? These questions have inspired modern theoretical frameworks like cosmic inflation, which posits that shortly after the Big Bang, the universe underwent a brief but exponential expansion, smoothing out irregularities and seeding the structure we see today. Inflation also predicts that what we observe is only a tiny fraction of a much larger, possibly infinite universe. Key discoveries continue to reshape our understanding. In the late 1990s, observations of distant supernovae revealed that the expansion of the universe is accelerating, not slowing down as previously thought. This led to the introduction of dark energy, a mysterious force that permeates all of space and counteracts gravity on cosmological scales. Today, dark energy is estimated to make up about 68% of the universe, with dark matter comprising another 27%. Leaving ordinary matter-everything, we concede only 5%. This realization shattered our assumption that we understood most of what the universe contains and opened a new frontier in physics. The search to identify the nature of dark matter and dark energy has become one of the most pressing goals in modern cosmology. Particle physics experiments like those at CERN's Large Hadron Collider, space-based observatories like Euclid and the Vera Rubin Observatory, and cosmic surveys like the Dark Energy Spectroscopic Instrument, DESI, are all part of a global effort to unravel these mysteries. Meanwhile, gravitational wave observatories like LIGO and Virgo have added a new dimension to our observational toolkit, detecting ripples in space-time from cataclysmic events like black hole mergers. These instruments have already confirmed key predictions of general relativity and promise to reveal more about the invisible universe. Our understanding of the cosmos has also been enriched by theoretical breakthroughs. Quantum mechanics and relativity, though still not unified, offer different lenses through which to examine the universe. Theories like string theory and loop quantum gravity attempt to reconcile these two pillars of physics and offer potential insights into the earliest moments of the universe. Some models propose that the Big Bang was not the beginning, but a transition, a bounce from a previous contracting phase, or the result of colliding brains in higher dimensional space. These ideas are still speculative but offer exciting possibilities for what might lie beyond our cosmic horizon. Even as we push the boundaries of knowledge, the human perspective remains central. The historical evolution of cosmology is not just a tale of facts and formulas, but of shifting worldviews. From the Earth-centered cosmos of antiquity to the multiverse theories of today, our place in the universe has continually changed. Each discovery humbles us while revealing new layers of complexity. We are no longer at the center, nor are we at the edge. We are participants in a vast, dynamic system whose full nature we may never fully grasp. And yet, our capacity to ask, to explore, to imagine, and to model remains our most powerful tool. The journey from ancient stargazing to space telescopes and quantum fields tells a larger story, one of curiosity, persistence, and a refusal to accept the limits of current understanding. It is a story that connects generations and cultures across millennia, united by a common desire to understand where we are, how we got here, and what lies beyond. The observable universe is both a scientific construct and a metaphor, a bubble of knowledge always expanding, always chasing the light from distant realms. It reminds us that we are finite beings in an infinite mystery, and that every answer we find is only a gateway to a deeper question. Why should anyone care about what lies beyond the stars, galaxies, and the farthest reaches of space we can see? Why should the vast, cold emptiness of the cosmos matter to someone sitting on Earth, drinking coffee, scrolling through their phone, or walking home after work? Because it speaks directly to the core of what it means to be human. It touches something ancient and timeless inside us, the need to understand, to explore, to find meaning. From the first time a human being looked up at the sky and wondered what those lights were, something stirred in our species that has never faded: curiosity. The universe is not just out there, it's also in us. We are made from its elements, born from the ashes of ancient stars, living on a pale blue dot, orbiting a relatively ordinary star in one galaxy among trillions. But even that extraordinary reality doesn't fully capture why people care. We care because the universe is both beautiful and terrifying, limitless and personal. It represents everything we don't yet understand, and everything we dream of becoming. There's an almost spiritual awe that comes with thinking about the scale of the cosmos. When we realize that the light we see from distant galaxies has been traveling for billions of years, it puts time into a different perspective. Our entire lives soar joys, losses, struggles. Victories happen in the blink of a cosmic eye. And yet, despite that insignificance, we are the ones able to perceive this vastness, to contemplate infinity, to wonder about what's out there. That ability makes us powerful. It means we're not just passengers on this ride through space. We're conscious observers of the grandest show ever staged. But that realization brings more than wonder, it also brings fear. What if we're alone? What if there's nothing beyond this? What if all our searching leads to silence? The idea of a cold, indifferent universe can feel deeply unsettling. The notion that there may be no ultimate purpose, or that we are just a temporary anomaly in a meaningless void, is a heavy emotional weight. And yet, even within that fear, lies something profound. A motivation to create meaning, to seek connection, and to leave a mark. When people ask what's beyond the universe, they're rarely asking about equations or redshift data. They're asking if there's something more than this, more than jobs and cities and daily routines. They're asking if there's a reason, if there's a purpose, if there's hope beyond what we can see. The cosmic void becomes a mirror for our inner lives. We project our longings onto the stars. The unknown becomes a canvas where we paint our fears and our fantasies. We search the sky for alien life, not just because we're curious about biology, but because we're aching for confirmation that we're not alone. We study the birth and death of stars, not just to learn physics, but to understand where we come from and where we're going. In every question about the universe is an echo of deeper, more personal questions. Who am I? Why am I here? What happens after I die? What is the point of all this? The cosmos doesn't offer simple answers, but it does offer perspective. It reminds us that we're part of something bigger, that even our smallest actions ripple through time and space, that we belong to a universe that, for all its vastness and violence, also gave rise to life, beauty, and consciousness. There is also hope in the stars. The idea that the universe may be filled with other civilizations, other beings looking up at their own skies and wondering the same things. That's not just a scientific hypothesis. It's a romantic idea. It gives people a sense of possibility. Maybe we're not the first, and maybe we won't be the last. Maybe life is more common than we thought. Or maybe, in the great silence of space, we'll realize that life is rare and precious and that we must protect it at all costs. The emotional weight of the cosmos is carried in the stories we tell. From ancient myths of constellations to modern space operas, we've always used the stars to make sense of our struggles, our identities, and our place in the universe. The cosmos becomes a metaphor for love, for loneliness, for ambition, for freedom. We imagine heroes journeying across galaxies because deep down, we long to transcend our limitations. We dream of colonizing other worlds because we dream of starting over, of escaping the broken parts of this one. We build telescopes and spacecraft not just because we can, but because we must. Because looking outward is how we learn to look inward. Even the darkness of space teaches us something. The cosmic void isn't just a region of emptiness, it's a space full of unanswered questions. And in those questions, we find motivation. The vast unknown doesn't paralyze us, it energizes us. It fuels science, art, philosophy. It forces us to confront the limitations of our knowledge and the expansiveness of our imagination. The fear of the unknown is real, but so is the exhilaration. The moment we understand that we don't know everything is the moment we truly begin to learn. And maybe that's why people care so deeply, because the universe gives us permission to wonder. It gives us a place to be uncertain, to be curious, to be amazed. It gives us something to reach for, both literally and metaphorically. When you stare into the night sky, you're not just seeing stars, you're seeing the past. You're seeing light that left its source before humans even existed. And that realization that we can catch photons that have traveled through eons of cosmic history feels like a form of time travel. It connects us to something eternal. In that moment, the boundaries between the scientific and the spiritual begin to blur. We become both dust and miracle, both insignificant and irreplaceable. Our lives are short, but our questions are long. And the universe, with all its mystery and silence, becomes the stage on which those questions echo. In a world that often feels chaotic, divided, and overwhelming, the stars offer a kind of peace. They remind us of continuity, of beauty, of something beyond ourselves. They are always there, unchanged by our daily struggles, quietly burning in the distance. That constancy can be comforting. It can also be inspiring. It tells us that even in the darkest of nights, there is light that has traveled for billions of years just to meet your eyes. That fact alone can bring people to tears, not because it's sad, but because it's sublime. It shows that the universe is not a cold place without meaning. It's a place where meaning is possible, even if we have to create it ourselves. There's also a sense of responsibility that comes with cosmic awareness. The more we learn about the fragility of life, the rarity of Earth-like planets, the thin line that separates habitable from hostile environments, the more we realize how precious our planet is. Looking out teaches us to look back, to see Earth, not as a set of nations or borders, but as a shared home suspended in space. The famous pale blue dot image captured by Voyager 1 in 1990 encapsulated this feeling perfectly. In that tiny speck of light, Carl Sagan said, was everyone we ever knew, every life lived, every joy and sorrow, every religion, every government, every hero and coward. That photo didn't just show Earth, it showed perspective. And perspective breeds empathy. It forces us to care not just about space, but about each other. So why care about what lies beyond the observable universe? Because it's not just about physics or astronomy. It's about us. It's about our place in a grand, unfolding story that began long before we arrived and will continue long after we're gone. It's about realizing that the questions we ask about the stars are the same questions we ask about ourselves. To care about the cosmos is to care about possibility, about meaning, about connection. It's to recognize that we are part of something bigger and that our small lives are still worth everything. It's to feel awe not just because the universe is vast, but because we are able to feel that awe at all. In the end, the universe does not owe us answers. It doesn't have to make sense or explain itself. But the fact that we can ask, that we can search, that we can build stories and sciences that push the boundaries of what we know, that's the gift. That's the emotional core of it all. It's not the final destination that matters, it's the journey, the wonder, the courage to look into the void and say, we are here. We are small, but we see. We are fleeting, but we dream. We are alone, perhaps, but we care. And maybe that's enough. Maybe that's everything. What do you believe lies beyond everything we can see? When you stare into the night sky, do you imagine it going on forever? Do you think it ends somewhere? What if it doesn't end at all, but loops back on itself like a cosmic circle? Or what if the space we see is just one of countless realities, stacked or floating in a grand multiversal sea? These questions are not just scientific curiosities, they are deeply human ones. They reach into the core of how we understand reality, how we define existence, and how we fit into the incomprehensible scale of everything. The mystery of what lies beyond the observable universe is not only a question for physicists and astronomers, but for anyone who has ever looked up and wondered. It is a question that crosses cultures, generations, and ideologies, because it touches something that science alone cannot explain or need to make sense of the unknown, to define the borders of our reality, and to ask, is there something more? Imagine for a moment that tomorrow we discovered irrefutable evidence of a parallel universe, one where time flows in reverse or where gravity behaves differently. How would that reshape your view of everything you thought was certain? Would you still see your life the same way? Or would it stir something deeper, a sense that our rules, our logic, our meaning may not be as fixed as we assume? Or suppose we prove that the universe is infinite, with infinite variations of matter, of life, of consciousness. Would that make your existence feel more significant or more fragile? These possibilities are not merely science fiction, they are active subjects of debate, of research, of imagination. They challenge us not only to think beyond, but to feel beyond. Because when the foundations of our reality are questioned, it shakes everything that rests on them: identity, purpose, morality, destiny. So ask yourself, why does this matter? Why should the boundaries of the observable universe concern people who are dealing with real-life struggles on Earth wars, climate change, economic uncertainty, or personal hardships? The answer is not escapism, it's transformation. The very act of thinking cosmically can change how we live locally. It brings humility. It reminds us how small we are, but not in a diminishing way, in a liberating way. It allows us to let go of the illusion of control and see life as part of a wider dance, one that has been going on for billions of years and will continue long after us. It encourages empathy, because when we realize we all share the same fragile rock in an indifferent universe, divisions start to feel smaller. It also sparks ambition, because if the universe is truly this vast, then the possibilities for exploration, for creation, for understanding are almost endless. And that means our choices, our actions, our innovations matter. What new discoveries might lie just over the horizon? Could the next telescope capture evidence of cosmic structures beyond our current limits? Could the detection of gravitational waves from ancient cosmic events give us clues about dimensions or realities outside our own? Could artificial intelligence analyzing deep space data uncover patterns we've never seen? Could we one day simulate entire universes within supercomputers, each obeying slightly different physical laws, and find echoes of our own existence among them? Every new discovery has the potential to break the frame of our current understanding. Just as Copernicus and Galileo rewrote our place in the solar system, and just as Einstein redefined space and time, the next great leap could redefine what it means to exist. It could force us to rethink consciousness, causality, even the nature of time itself. And those aren't abstract ideas, they affect everything from philosophy to technology, from ethics to culture. If we discovered a universe beyond ours, what would that do to religion, to spirituality, to how we view life and death? Would it confirm ancient intuitions about other realms? Or would it challenge long-held beliefs? Would it unite people in awe or divide them in interpretation? And if we found that our universe is not the only one, but one of many that make us less unique or more? Does it dilute our meaning or deepen it? These are not easy questions, and they are not meant to have simple answers. They are meant to open doors, to start conversations, to make you sit back and ask, what if? This is why we must engage with these mysteries, not just passively, but actively. Ask your own questions, challenge your own assumptions, share your ideas with others. What do your friends think lies beyond the edge of the universe? What do your parents believe about infinity? What would your younger self have imagined? These are the kinds of conversations that light fires, not because they give certainty, but because they open space for curiosity, for creativity, for connection. You don't have to be a scientist to participate. You just have to wonder, to care. To be willing to explore not only the universe, but your own mind. Think about the potential impact of a breakthrough in understanding the cosmos. It wouldn't just change science, it could change culture, consciousness, and maybe even civilization itself. Just as the photograph of Earth from space helped spark the environmental movement by showing us our planet's vulnerability, so too could the discovery of a multiverse shift how we think about choice, fate, and reality. What if your life is one path among many? What if every decision you make branches into other versions of reality? What if you are one of infinite versions of yourself, each living out different possibilities? These ideas may sound wild, but they stem from real interpretations of quantum mechanics and cosmological models. They are being taken seriously, not because they are convenient, but because they are consistent with the mathematics and with the data we've collected so far. And yet, even if none of these theories are ever proven, the process of questioning still enriches us. It keeps us from becoming complacent. It keeps science alive, not as a fixed body of facts, but as an evolving dialogue with nature. It also keeps imagination alive, which is equally important, because imagination is what drives exploration in the first place. It's what allows us to go beyond what we know, into what we might know. The line between scientific discovery and creative inspiration is thinner than we think. Einstein imagined riding on a beam of light before he wrote the theory of relativity. Kepler described the harmony of the planets as music. Galileo wrote in dialogue form to reach wider audiences. And today, the most cutting-edge scientific questions are often explored through simulations, metaphors, and visualizations that require deep creative thinking. So here's your invitation. Ask questions that scare you. Ask questions that excite you. Ask questions that don't have answers yet. What is time, really? What was before the Big Bang? Can the universe think? Is consciousness something the universe does, or just something we do inside it? What if the universe is conscious? What if it's not? What does it mean that we can ask these questions at all? These are not distractions from real life, they are reflections of it. They help you understand yourself, your place, your potential. They train your mind to move between scales from the molecular to the cosmic, from the personal to the universal. And that mental flexibility can serve you in everything, from relationships to work to how you handle uncertainty. Every discovery begins with a question, and every revolution in thought begins with the courage to challenge the current answers. We live in a time when the boundaries of knowledge are expanding faster than ever before. We have more access to information, more powerful tools, and more global conversation than any generation in history. That means you are not just a witness to this unfolding mystery, you are part of it. Whether you're a student, an artist, a scientist, a gamer, a dreamer, a skeptic, or someone just trying to get through the day, you have a role in shaping how we think about the cosmos. You can ask the question that leads to the next idea. You can build the story that inspires the next mind. You can be the person who reminds others that it's okay not to know everything, and that sometimes the best part of the journey is the mystery itself. We may never see beyond the observable universe. We may never touch another reality or map the edge of space-time. But we can ask, we can imagine, we can talk, and in doing so, we bring the unknown closer. We make it part of our lives, our culture, our story. Because the real edge of the universe isn't out there, it's in here, in what we choose to explore, to believe, to pursue. So what do you think? What lies beyond the universe? Do you believe in infinity? In other dimensions? In unseen world? Or do you think this is all there is, and that's enough? Whatever your answer, know that the conversation matters, that your voice matters, that the universe isn't just a thing to be observed, it's a thing to be shared. Take this moment, this thought, this curiosity, and pass it on. Ask your friends, post your questions, join a discussion, make a video, write a story. Let your imagination take you to the edge of the known and then go further. Because that is how discovery begins. Not with certainty, but with wonder. Not with answers, but with questions. And not alone, but together. We are explorers, not just of space, but of meaning. And the most powerful telescope we will ever have is still the human mind, aimed not only at the stars, but at the mystery of being itself. The silence is absolute. There is no air in space to carry sound, no ground to touch, no up or down to orient yourself. Just a vast, weightless ocean of blackness stretching in every direction, broken only by the distant, ancient light of stars. Each point of light is a sun, many with their own planets, their own histories, their own mysteries. You float, in imagination, if not in body, thousands of light years above the galactic plane, and you see the Milky Way not as a smudge of light in the night sky, but as a massive spiral of stars turning slowly like a great cosmic pinwheel. You realize that it is made of hundreds of billions of suns, all swirling around a supermassive black hole hidden at its Korean invisible engine of gravity, millions of times the mass of our own star. The spiral arms shimmer with clusters of newborn stars, glowing pink from the radiation of hot hydrogen gas. Dusty lanes cut through the arms like scars, hiding cold nurseries where new stars are still forming in silence. And beyond that, beyond our galaxy are trillions more. This is the stage upon which the great cosmic story unfolds. Between the galaxies lie void colossal regions of space so empty they defy comprehension. These are not merely gaps, but vast chasms, stretching tens of millions of light years across, where almost no matter exists. They form the dark backdrop of the cosmic web, a structure so large that galaxies become like atoms in a molecule. The cosmic web is not random. It has a shape, a flow, a structurous skeleton of the universe traced by the invisible hand of gravity and dark matter. Filaments of galaxies form long strands that intersect at nodes, like cosmic cities connected by glowing highways. And in between those threads lies nothing, a haunting, echoing nothingness that is not truly empty, but filled with dark energy, unknown force that stretches the fabric of space itself, pushing galaxies apart at an accelerating pace. You are now moving deeper, seeing not with your eyes, but with your mind, guided by science and imagination. You see quasars, brilliant beacons of light from the early universe, powered by black holes devouring entire stars and converting them into pure energy. You witness nebulae, clouds of gas and dust shaped like ghosts, hands, butterflies, and dragons. Their colors enhanced by telescopes to show the radiation of different elements: glowing red hydrogen, bright green oxygen, deep blue sulfur. You approach the remnants of exploded star supernovae that have spread the elements of life into the cosmos: carbon, nitrogen, oxygen, iron. You realize that these violent deaths are the reason we exist. Our bodies are made of stardust, assembled from the debris of long-dead suns. Time in space does not flow as it does on Earth. As you drift past a pulsar, rapidly spinning neutron star left behind by a supernova, you see it flash with incredible precision, spinning dozens or hundreds of times per second, each flash a beat in the rhythm of the cosmos. Around it, space bends. Gravity becomes so strong that light itself curves. This is the domain of general relativity, where Einstein's equations describe how mass tells space how to curve, and curved space tells matter how to move. You approach a black hole, not just any black hole, but 1 millions of times the mass of the Sunday. Its event horizon is a one-way surface, a boundary beyond which nothing returns. As you get closer, time slows. Light from stars behind it is bent and magnified, forming a glowing ring called the Einstein lens. The black hole doesn't pull like a magnet, it warps everything around it, including reality itself. This journey is made possible not through spacecraft, but through the minds of cosmologist scientists who dedicate their lives to understanding the universe. These are the key players in this unfolding story. Thinkers like Stephen Hawking, who explored the behavior of black holes and proposed that they emit radiation. Alan Guth, who developed the theory of cosmic inflation, explaining how the universe expanded faster than light in its first fraction of a second. Vera Rubin, whose observations of the rotation of galaxies provided some of the earliest and most compelling evidence for dark matter, a mysterious substance that outweighs normal matter 5 to 1, yet cannot be seen directly. George Smoot and John Mather, who measured the cosmic microwave background radiation with exquisite detail, mapping the faint whispers of the Big Bang and winning the Nobel Prize for revealing the birthmarks of the cosmos. Today, others continue their work, Researchers using the James Webb Space Telescope to peer further back in time than ever before, capturing galaxies forming just a few 100 million years after the Big Bang. Teams working with LIGO and Virgo detect gravitational waves ripples in space-time caused by collisions of black holes and neutron stars, providing a new way to observe the universe. Scientists at CERN seek to understand the fundamental particles and forces that shaped the early universe. Their work is not just academic, it is poetic, philosophical, and profoundly human. They are explorers not of land or sea, but of truth itself. They test the boundaries of the knowable. They navigate a universe where light takes billions of years to cross a galaxy, where the smallest particles and the largest structures obey the same mathematical principles, and where every answer leads to deeper questions. You now drift beyond even the galaxies, beyond the deep field images of telescopes, past the redshifted light that tells us how fast the universe is expanding. You reach the edge of the observable universe, not a wall, but a horizon. It marks the limit of what light has had time to reach us since the Big Bang. Beyond that line is not necessarily nothing, but rather something we cannot yet see and may never see. Perhaps it is more of the same, more galaxies, more stars, more voids, or perhaps it is different in edge, where the rules change, where space ends, where other universes begin. This is the great unknown. This is where science meets wonder. The atmosphere here is not cold, despite the vacuum. It is electric with possibility. The silence is filled with the hum of equations, the pulse of gravitational waves, the glow of radiation from the birth of time. This place is not empty. It is alive with questions. What came before the Big Bang? Was there a before? Is time a loop, a line, or an illusion? Are there other universes with different laws of physics, where light behaves differently, or where stars never formed? Is the universe infinite, or does it fold back on itself like a hypersphere? Can we one day escape the boundaries of our own reality? Or are we forever locked within this cosmic bubble? You feel the scale now not in numbers, but in emotion. It is awe, a quiet, shaking kind of awe that humbles and elevates at the same time. It is mystery, the kind that invites you to think harder, dream further, and speak softer. And it is scientific curiosity, the fuel of all discovery, the spark behind every telescope pointed upward and every formula scratched into a notebook. This feeling is not reserved for scientists alone. It belongs to anyone who has ever asked a question they couldn't answer, anyone who has ever looked at the stars and felt small, not in a despairing way, but in a way that opens the heart. Because to be small in a vast universe is not to be insignificant. It is to be rare, to be precious, to be alive at the one moment in cosmic history where the universe has become aware of itself through you. The universe is not static. It is dynamic, evolving, expanding. The light from the earliest galaxies is still on its way to us, like messages written in the language of photons, carrying stories of creation across space and time. And we are still listening, still watching, still learning. We build better instruments, write better models, ask better questions. And as we do, the universe opens, slowly, like a flower blooming in the void. Each discovery is a petal, each breakthrough a scent. We are not just in the universe, we are of it. The atoms in our bodies were forged in ancient stars. The hydrogen in our water was born in the first moments after the Big Bang. The neural patterns in our brains reflect the networks of galaxies that span the cosmos. The universe is not something separate. It is a mirror, a source, a destination. As you return from this journey of imagination, you carry with you a sense of atmosphere that is impossible to forget. You feel the weightlessness of thought, the vastness of inquiry, the pull of wonder. You know that there are still mysteries waiting in the dark, the nature of dark matter, the fate of the universe, the origin of the laws that govern it. But you also know that the unknown is not something to fear. It is something to embrace. It is the wellspring of every great idea, every act of courage, every moment of insight. And in that space between the known and the unknowable, we find not just science, but meaning. So let this atmosphere linger. Let it fill the spaces between your thoughts. Let it guide your curiosity, your questions, your sense of connection. For the universe is not a place we visit. It is the very air of our imagination. And the journey into it is not measured in distance, but in depth, in courage, in awe. We dream of discovery. We dream of finding the edge of the universe, of standing at the final line where space ends or where another realm begins. But as we venture deeper into the cosmos through telescopes, equations, and thought experiments, a haunting truth begins to echo louder through the corridors of science. We may never find the true edge, not because we're not smart enough or advanced enough, but because the very structure of reality may forbid it. There is a kind of conflict brewing, not in the stars, but in the equations that govern Thema, quiet but profound tension between what we believe the universe should be and what it stubbornly continues to reveal. Every major leap in understanding brings with it a whisper of contradiction, a fracture in logic, a glimpse of something irreconcilable. The first signs of this conflict began with our definitions. What do we mean by edge? Is it a physical boundary like a wall, or a conceptual limit like the horizon? In our everyday experience, everything has a shape, a beginning and an end. A room has walls, a continent has shores, a planet has a surface. But when we ask, where does the universe end? We are trying to apply our terrestrial instincts to something that may not conform to them at all. The universe might be infinite not because it stretches forever in one direction, but because space itself is curved and loops back on itself, like the surface of a sphere in 3 dimensions, or a higher dimensional torus. In such models, you could travel in one direction forever and eventually return to where you began, never encountering a true edge, only the illusion of endlessness. But if the universe is infinite, it challenges everything we know about conservation, probability, and meaning. If there are infinite versions of you, infinite histories, infinite outcomes, do you define identity, choice, or consequence? And if the universe is not infinite, but finite and expanding, then where is it expanding into? What lies outside? Is outside the universe a coherent idea or a philosophical mirage? These questions have no definitive answers, and yet they form the architecture of our deepest inquiries. They are not obstacles in our path, are the path. And as we attempt to walk it, we encounter not just mystery, but paradox. One of the most disquieting signs that our understanding may be fundamentally limited is the disconnect between general relativity and quantum mechanics. General relativity governs the motion of planets, the warping of space-time, the expansion of the universe. Quantum mechanics governs the behavior of atoms, particles, and energy on the most microscopic scales. Both are extraordinarily successful within their domains. Both have passed every experimental test we've thrown at them. And yet, when we try to combine them, when we try to describe, for example, what happens at the center of a black hole, or at the moment of the Big Bang, these two pillars of physics explode into contradiction. They give infinite answers. They break down. They argue with each other. The very act of describing the totality of the universe, a cosmos that began at a single point of extreme density and now stretches into incomprehensible distances, requires a unified theory of everything. And yet, that theory remains elusive. This suggests not only a technical challenge, but a deeper possibility that the universe is built in a way we are not yet equipped to describe. Paradoxes multiply the further we go. The measurement problem in quantum mechanics implies that particles exist in a superposition of states until observed, raising questions about the role of consciousness in shaping reality. The information paradox in black hole physics suggests that information about matter swallowed by a black hole is destroyed, violating the laws of quantum mechanics, which insist that information must be conserved. The horizon problem in cosmology wonders how distant parts of the universe, now billions of light years apart, appear so uniform in temperature and structure, despite never having had time to exchange information. Cosmic inflation, a rapid expansion of space in the early universe, was proposed to resolve this, but inflation theory itself opens the door to the multiverse, to a landscape of countless other universes where our laws of physics may be statistical accidents, not universal truths. These paradoxes are not merely academic. They suggest that our tools may be insufficient. Even with the best telescopes, we are limited by the speed of light. We can only see as far as light has had time to travel since the beginning of the universe, about 13.8 billion years. But because the universe has been expanding, The true radius of the observable universe is about 46.5 billion light-years. That's as far as we can see. Beyond that, galaxies exist we're almost certain, but their light hasn't had time to reach us, and it never will. If the expansion of space continues to accelerate, driven by dark energy, these regions are not just dark, they are inaccessible. They are cut off, beyond the cosmic event horizon. Even if we waited forever, their light would never arrive. And so we are trapped not by glass walls, but by the geometry of the cosmos itself. We can model what might be beyond, but we cannot verify it. We can simulate other universes on supercomputers, but we cannot visit them. We can imagine the multiverse, but we cannot test it. At some point, our questions run up against the limits of observation. We are fundamentally empirical creatures. We need data, but the universe does not promise to give us all of it. Some answers may lie forever beyond our reach, hidden not because they are mysterious, but because they are truly unobservable. Even in our own universe, we face practical limits. The cosmic microwave background radiation is the oldest light we can see, dating back to about 380,000 years after the Big Bang. Before that, the universe was opaquely a glowing fog of plasma. We can infer what happened earlier through models, but we cannot observe it directly. Our instruments cannot pierce the veil of the first few moments of time. And the more we study dark energy and dark matter, the two dominant components of the cosmos, the more we realize we have no idea what they really are. Dark matter is invisible, detectable only through its gravitational influence. Dark energy is even more elusive, inferred only by its effect on cosmic acceleration. Together, they make up 95% of the universe. That means everything we've ever studied, all the stars, planets, and galaxies, comprise only 5%. We are children studying a beach, marveling at the sand, while the ocean remains invisible and vast before us. This is the shape of the conflict, a universe that reveals just enough to provoke endless curiosity, but withholds the full picture, perhaps permanently. It is not a conflict with enemies or borders, it is a conflict of epistemology. What can we know? What is knowable? How do we define understanding in a cosmos that may include realities we can never access, dimensions we can never sense, and laws we may never discover? And more urgently, how do we continue the pursuit of knowledge when the path forward grows ever more speculative? Science, at its best, thrives in this tension. The limitations are not walls, they are invitations. They show us where to look next. They challenge us to invent new tools, new methods, new philosophies. The paradoxes are not failures. They are signposts, pointing toward deeper truths. But they also serve as warnings. They remind us that certainty is a luxury the universe rarely affords. That what we think we know today may be overturned tomorrow. That our models, however elegant, are still maps, not the territory. And that the true nature of reality may be more strange, more beautiful, and more unknowable than we dare imagine. This growing uncertainty is not cause for despair, it is cause for humility. The conflict does not mean we should stop asking. It means we must ask more carefully, more imaginatively, with greater courage and greater respect for the mystery. Every new generation of cosmologists inherits this challenge. They build better instruments, refine their models, debate interpretations. They know that they are part of a continuum, a relay race across centuries, from Copernicus to Newton, from Einstein to Hawking, from the pioneers of radio astronomy to the engineers designing interstellar probes. The story of cosmology is one of relentless curiosity in the face of increasing mystery. The truth is, the universe is under no obligation to be simple. It is not required to make sense to us. If it has a true edge, it may be beyond our comprehension. If it doesn't, then we must accept that our deepest questions may have no final answer. That is the quiet battle being fought beneath the surface of science, the struggle between the limits of what is and the endlessness of what we wish to know. And yet, that struggle defines us. It is what makes science human. It is what makes wonder powerful. And it is what ensures that even if we never reach the edge, we will always keep moving forward. There is a silent war unfolding in the heart of cosmology. A battle not between people, but between ideas, between the deepest equations of physics and the quiet but unrelenting voice of the observable universe. At the center of this conflict lies a deceptively simple question: does the universe have an edge? The very act of asking it splits the field into opposing camps. Some believe the universe is infinite, boundless in space and time, with no beginning or end in any traditional sense. Others believe it is finite yet unbounded, curving back on itself like the surface of a sphere or a higher dimensional object. Still others believe we cannot know, that our instruments and models are insufficient to ever resolve the question. These disagreements are not trivial. They define the future of science. They shape how we interpret data, how we build telescopes, how we construct equations. They influence everything from quantum field theory to the way we imagine the ultimate fate of existence itself. This is not just a technical debate, it is the very soul of cosmology pulling itself apart. At the heart of this tension is the fundamental incompatibility between our two most successful physical theories, general relativity and quantum mechanics. General relativity, Einstein's crowning achievement, describes the behavior of gravity on large scales. It tells us how planets orbit stars, how light bends around massive objects, how the universe itself evolves over time. Quantum mechanics, on the other hand, governs the subatomic world. It describes the probabilistic nature of particles, the uncertainty of measurement, and the strange duality of waves and matter. Both theories are exquisitely precise. Both have been tested countless times and never found lacking. And yet, when we try to combine them, when we attempt to describe regions of extreme density, like black holes, or the instant of the Big Bang, they collapse into contradiction. General relativity predicts smooth, continuous curves in the fabric of space-time. Quantum mechanics demands granularity, fluctuations, and uncertainty. The result is mathematical chaos, infinities that can't be resolved, singularities that defy logic, paradoxes that challenge the foundations of physics. This theoretical war bleeds directly into the question of the universe's shape and extent. Is the universe finite or infinite? Both answers carry profound consequences. If it is infinite, then it has no edge, no center, no ultimate boundary. That means there is no special place, no privileged vantage point. Every point is as central as any other. In an infinite universe, every possible configuration of matter eventually repeats, not because of mysticism, but because of mathematics. Somewhere, unimaginably far away, there could be another planet exactly like Earth, down to the last molecule. Somewhere else, another, you might be reading these words under slightly different stars. This is the implication of infinity, not just vastness, but repetition. But infinity is a dangerous concept. It defies measurement. It resists probability. It introduces paradoxes that make scientific predictions impossible. Cosmologists are wary of infinity, not because it's philosophically troubling, but because it breaks the machinery of science. If, instead, the universe is finite, then we are left with new puzzles. What lies beyond? If space curves back on itself, then perhaps traveling far enough in one direction would eventually bring you back to your starting point, though not in any time frame relevant to human experience. This kind of closed universe solves the problem of infinity, but introduces its own tensions. Observational data from the cosmic microwave background radiation, galaxy distributions, and other measurements suggest the universe is very nearly flat. Not perfectly flat, but so close that the distinction is difficult to measure. In theory, a flat universe could be infinite or could wrap around in subtle ways that we can't yet detect. But the point remains. Every observation we make is interpreted through a lens of theory, and our theories are in conflict. Nowhere is this more obvious than in the clash between theoretical models and observable evidence. For decades, the Big Bang model has dominated cosmology. It is based on the observation that galaxies are moving away from each other, that the universe is expanding, and that it originated in a hot, dense state nearly 14 billion years ago. This model is supported by a wealth of data: the redshift of galaxies, the abundance of light elements, the cosmic microwave background. And yet, even within this triumphant model, cracks have formed. To explain why the universe appears so uniform across vast distances, cosmologists proposed inflation, a brief period of exponential expansion that occurred a fraction of a second after the Big Bang. Inflation solves many problems, but it introduces new ones. It predicts that our universe may be just one bubble in a vast, inflating multiverse concept that cannot currently be tested and may never be. This is where the battle sharpens. Some cosmologists argue that science must remain anchored to what is observable. They warn against drifting into metaphysical speculation, against building castles in the air from beautiful equations with no experimental foundation. Others argue that we must follow the math wherever it leads, even if it takes us beyond the observable, into realms we can never see. The multiverse, they say, is not fantasy, it is a logical extension of inflationary theory and quantum mechanics. To deny it would be to ignore where the evidence points, even if that evidence is indirect. This rift is not just about modals, it is about the very philosophy of science. What counts as evidence? What counts as truth? What role does observation play when the most profound truths may be forever beyond our instruments? The struggle to define the universe's edge also confronts technological limits. The observable universe is bounded by the cosmic horizon, the maximum distance light has traveled since the beginning of time. Anything beyond that lies forever out of reach. Even if galaxies exist there, their light has not had time to reach us. If the expansion of the universe continues to accelerate, driven by dark energy, then more and more of the cosmos will slip beyond our horizon. One day, distant galaxies will become invisible in it because they vanish, but because their light will never reach us. The universe will seem to empty itself out, leaving only the local group of galaxies still visible. In such a future, observers will not be able to see the Big Bang's afterglow or detect cosmic expansion. They will be cosmologically blind, trapped in a shrinking sphere of knowledge. The irony is bitter. The more the universe expands, the less we will be able to see. This looming blindness adds urgency to the conflict. Time is not on our side. The information we seek may already be fading beyond our reach. And even now, what we see is filtered through instruments with limitations. Telescopes can only gather so much light. Data is interpreted through models with built-in assumptions. Every map we make of the cosmos is just a shadow of reality, shaped by human choices, constraints, and theories. We live in a moment of tension, where our ability to measure is still powerful, but where our models are beginning to drift beyond what measurement can confirm. Theories of extra dimensions, holographic universes, and mathematical landscapes filled with potential universes are breathtaking, but they are also untested and perhaps untestable. This is the growing fault line in cosmology, the desire to know more, colliding with the possibility that some things cannot be known. And yet, even in this tension, there is beauty. The clash of theories is not a sign of failure. It is the pulse of a living science. Every contradiction is a clue. Every paradox is a doorway. Every disagreement forces us to look again, to refine, to challenge, to deepen our understanding. The struggle is not only external, between models, but internal within each scientist, each thinker, each person who dares to contemplate the infinite. It is a battle between certainty and doubt, between ambition and humility, between imagination and rigor, and it is what drives progress. Consider the debates that rage between advocates of string theory and those who seek more empirical models. String theory posits that the fundamental particles are not point-like, but tiny vibrating strings existing in a 10 or 11-dimensional space. It promises unification of gravity and quantum mechanics, but it also exists in a vast landscape of possible solutions, each corresponding to a different universe with different physical laws. Critics argue that this is not science, but metaphysics, that if every outcome is possible, nothing is predictable. Defenders argue that this is what unification demands, that the theory is not flawed, but our understanding is incomplete. This is not just a scientific argument. It is a philosophical rift over the purpose and limits of science itself. Another front in the conflict is the question of initial conditions. Why did the universe begin in such a low entropy state? Why does it obey the laws it does? Is our universe fine-tuned for life, or is life simply a consequence of the parameters we happen to have? These questions touch not only on physics, but on deeper inquiries about existence. Some seek answers in the anthropic principle that we observe this universe because it is one in which observers can exist. Others recoil from this idea, seeing it as a retreat from explanatory power. They search for deeper laws, deeper reasons, but every answer seems to fragment into new questions, like a fractal that never ends. What if the universe has no edge? What if the question itself is a remnant of our limited perception of a species born on a spherical planet, surrounded by boundaries, conditioned to believe that everything must start and end somewhere? The possibility that the universe is truly boundless, without an edge, without a border, without a final frontier, is one of the most unsettling and profound ideas in all of science. It challenges the way we think not only about space, but about existence itself. It stretches our imagination and breaks the comforting symmetry of beginning, middle, and end. And it forces us to confront a cascade of consequences, each more radical than the last for physics, for cosmology, and for our deepest philosophical assumptions. In the language of modern cosmology, an edge is not necessarily a physical wall. Rather, it is a conceptual boundary, the furthest point we can observe, the end of causal contact, the furthest point light has traveled since the beginning of the universe. That boundary is real, in a practical sense, but it's not the edge of the universe. It's the edge of the observable universe, a bubble of visibility in an ocean of potential reality. If the universe has no edge, it may extend infinitely beyond what we can see, or it may wrap back on itself in ways that we can never detect. Either way, we must grapple with the implications of an endless, edgeless cosmos. First, we are forced to reevaluate the foundations of physics. Many physical laws, particularly those of classical mechanics and thermodynamics, evolved in a universe we thought was finite, predictable, and closed. But in a truly edgeless universe, the conservation of energy, the flow of entropy, and the definition of causality all take on new, complex dimensions. An infinite universe, for example, could contain infinite energy, infinite matter, and infinite possibilities. But how do you define probability in an infinite context? If every outcome happens somewhere, what does it mean to make a prediction? The very structure of the scientific method, hypothesis, prediction, observation, falsification, begins to erode when the playing field is infinite. Every test becomes uncertain. Every outcome may be both true and false, depending on your position in the cosmos. This creates a philosophical problem that borders on the existential. If the universe has no edge, then there may be no ultimate destination, no endgame, no outer shell to reach, no final veil to lift. That doesn't make the universe less beautiful, but it does make it more indifferent. It implies that we are not approaching a climax in our understanding, but rather sinking ever deeper into an endless ocean of questions. It suggests that the truth may always lie just out of reach, not because we are blind, but because there is no final truth to grasp, just layers of deeper understanding, infinite in scope and eternal in pursuit. This can be a disheartening realization for those who crave closure, who seek a theory of everything, or a moment of cosmological revelation. But for others, it is liberating. It means that the journey is the point, that curiosity is not a means to an end, but an end in itself. If the universe has no edge, then it also has no center. That means there is no special Placino location more important than another. Earth is not at the center. Neither is the Sunday, the Milky Way, or even our observable bubble. Every point in the universe sees itself as the center of its observable universe, surrounded by a sphere of visibility limited by the speed of light. This leads to a remarkable conclusion. The universe is isotropic and homogeneous on large scales. It looks the same in every direction, from every vantage point. This principle, known as the cosmological principle, has deep implications. It means that the laws of physics are the same everywhere. It means that no region of the universe is privileged. And it means that we are not the product of a special location, but of universal laws that operate with impersonal consistency. But this very consistency leads to unsettling philosophical consequences. If the universe is infinite and follows consistent laws, then everything that can happen must happen somewhere. Every particle arrangement, every physical configuration, every history must repeat an infinite number of times. This is not mystical speculation. It is the direct implication of mathematical infinity. Somewhere out there, there could be another Earth, another you, reading these same words under a slightly different sky. Somewhere else, there could be infinite versions of you who made different choices, lived different lives, met different people. This is the multiverse not as a parallel realm, but as an inevitable consequence of infinite space and matter. The psychological weight of this idea is enormous. It calls into question the uniqueness of everything we hold, their identity, memory, morality. If every possible version of your life is played out somewhere in the cosmos, does your choice still matter? If your life is just one node in an endless web of identical or nearly identical lives, does that diminish its meaning or enhance it? Some argue that this idea robs life of its significance. Others argue the opposite, that the very fact we are conscious of this infinite backdrop and still choose to live, to love, to create, makes our choices all the more heroic. We choose not because we are unique, but because we are aware. On a scientific level, the idea of an edgeless universe also compels us to question the origin of space and time. If the universe has no edge, then what caused it to begin? Or did it begin at all? The traditional Big Bang model describes a hot, dense state from which space and time expanded, but it does not explain what came before. In fact, the model breaks down at time zero. General relativity gives us singularities points of infinite density and curvature, but these are signs of mathematical breakdown, not physical reality. To move beyond this, we need new physics, quantum gravity, string theory, loop quantum cosmology. These are attempts to create a new framework that unites the large and the small, the continuous and the discrete. But none have yet delivered a definitive answer. Some models suggest that the universe could be eternal, with no beginning or end. Others propose a cyclical model, where the universe expands and contracts in an infinite loop. Others suggest our universe was born from the collision of higher dimensional branes, or from quantum fluctuations in a larger multiverse. Each of these ideas is bold. Each challenges our current models, and each highlights the growing need for new physics that goes beyond Einstein, beyond quantum field theory, beyond our current conceptual tools. We need new mathematics, new experiments, and perhaps even new ways of thinking, because the universe is telling us something that the old frameworks are insufficient. That the cosmos is not a machine to be mapped, but a living question to be experienced. If the universe has no edge, then space is not a container, but a fabric. It is not where things air, it is what things are made of. And if space has no boundary, then neither does potential. There are no limits to what can be discovered, or imagined, or created. But this too has consequences. The further we go, the more speculative our science becomes. Theories drift beyond testability. Models grow more complex. Some physicists worry that cosmology is approaching a metaphysical phase, where evidence is replaced by elegance, and testable predictions give way to aesthetic preferences. Others argue that this is the natural evolution of any deep science, that we must be willing to follow ideas beyond the limits of current observation, just as Einstein did, just as Newton did. This debate itself is one of the consequences of the edgeless universe. It pushes science to its philosophical limits. It forces us to define what science is and what it should be. Is it purely empirical? Is it allowed to explore the unobservable? Can we accept theories that are internally consistent but untestable? These are not idle questions. They determine funding, education, and the direction of entire fields. They determine how we teach the next generation to think about reality. And they determine whether science remains grounded in observation or floats into abstraction. And then, beyond science, there is the human question. What does it mean to live in a universe with no edge, no center, no destination? It means that we must create meaning, not find it. It means that the significance of our lives is not imposed by cosmic structure, but chosen by human will. This can be frightening, but it can also be empowering. It means that in an infinite universe, meaning is rare and, therefore, precious. It means that your life, however brief and small in cosmic terms, can be a lighthouse in the dark. It means that consciousness is not an accident, but a phenomenon that carries the weight of understanding in a universe that may otherwise be indifferent. In this way, the edgeless universe returns us to ourselves. It shows us not how vast space is, but how rare awareness is. Not how far we are from the edge, but how close we are to the center of our own experience. It forces us to ask not just where we are, but who we are and why we care. And so we return to the beginning not with answers, but with better questions. If the universe has no edge, then we must learn to navigate without borders. We must learn to think in curves, to reason in infinities, to accept the unknown not as failure, but as invitation. We must let go of finality and embrace the eternal unfolding of knowledge. The universe has no edge, but our understanding does. And that is where the journey begins. There comes a moment in every great journey when the traveler crests a hill, turns a corner, or emerges from the dark and sees something that changes everything. In the story of human exploration of the cosmos, that moment has come again and again, but perhaps never so dramatically as in the last few decades. What began as philosophical speculation about spheres in the sky and crystalline heavens has now become a data-driven search across billions of light years. And just when we thought we had found our footing in the stars, the universe shifted beneath us. This was the turning point, the moment we realized the cosmos is not only expanding, but accelerating. The moment we met dark energy, the moment our most successful models were no longer enough, and the moment we turned our gaze to new tools, new ideas, and a new understanding of our place in a universe more dynamic, mysterious, and astonishing than we had ever imagined. In the late 1990s, two teams of astronomers, the Supernova Cosmology Project and the High-Z Supernova Search Team, set out to measure how the expansion of the universe was slowing down. They expected to find evidence that gravity, over billions of years, had gradually decelerated the cosmic expansion that began with the Big Bang. To do this, they observed distant Type Ia supernovae, which serve as standard candles, exploding stars with known intrinsic brightness. By comparing their apparent brightness with their redshift, how much their light had been stretched by cosmic expansion, the astronomers hoped to plot the universe's deceleration curve. What they found stunned the world. The supernovae weren't dimmer because they were farther than expected. They were dimmer because they were accelerating away faster than anyone had predicted. The universe wasn't slowing down, it was speeding up. This was the revelation that changed cosmology forever. The acceleration meant that some unknown force, some anti-gravity, was driving the expansion of space itself. We named it dark energy, not because we understood it, but because we didn't. It accounted for nearly 70% of the total energy density of the universe. It wasn't matter. It wasn't radiation. It wasn't anything we could touch or see or contain. It was something fundamentally new. A pressure embedded in the vacuum of space, a feature of the cosmos that had lain hidden in plain sight for billions of years, only now revealed by the dying light of ancient stars. This discovery earned the 2011 Nobel Prize in Physics. But it also opened a rift in our understanding. For all our equations and models, for all our simulations and surveys, we still do not know what dark energy actually is. A cosmological constant? A new field? A flaw in general relativity? We're still asking, still searching. Yet even as this mystery deepened, our ability to look further and finer improved. The turn of the 21st century saw a revolution in astronomical technology. Ground-based observatories like the Very Large Telescope, VLT, in Chile, and the Subaru Telescope in Hawaii reached unprecedented levels of resolution and sensitivity. But the real breakthrough came from above the atmosphere, from space-based telescopes freed from the distortion of Earth's air. The Hubble Space Telescope, launched in 1990, transformed our understanding of the universe. With it, we captured the iconic deep field and ultra-deep field images-long exposures that revealed thousands of galaxies in a tiny, previously empty patch of sky. These galaxies were not local. They were ancient. Some dated back to when the universe was less than 1 billion years old. We were, in effect, seeing the infant cosmos with our own eyes. These images were more than beautiful, they were revelatory. They showed that galaxies formed earlier than expected and in complex, diverse forms. They hinted at structures we didn't predict. They confirmed that the universe is filled not with a chaotic distribution of stars, but with an intricate web of matter galaxies organized into filaments, sheets, and vast voids. This cosmic web suggested a deeper architecture to the universe, one governed not only by visible matter but by the elusive influence of dark matter and the invisible push of dark energy. Every pixel in those Hubble images whispered a new story, a new chapter in the book of cosmic evolution. Then came the Planck satellite, launched by the European Space Agency. Planck provided the most precise map of the cosmic microwave background, the faint glow left over from the Big Bang. This map offered a snapshot of the universe when it was just 380,000 years old, still a hot soup of particles and radiation. From this map, cosmologists derived astonishingly precise values for the age, composition, and geometry of the universe. It became clear that only about 5% of the universe consists of ordinary matter, atoms that make up stars, planets, and people. The rest is composed of dark matter, 27%, and dark energy, 68%. These were no longer fringe ideas, they were the majority. The dominant ingredients of the cosmos were invisible, unknowable, and yet undeniable. Meanwhile, the James Webb Space Telescope, JWST, launched in late 2021, began to rewrite everything once more. With its infrared capabilities, JWST peered even deeper into the early universe, observing galaxies from just 300 million years after the Big Bang. It found massive, complex galaxies forming far earlier than our models predicted. These galaxies appeared too large, too evolved, too structured for the cosmic age in which they existed. This raised new questions. Was our timeline of galaxy formation wrong? Were the rules of structure growth different in the early universe? Or were we missing something fundamental about gravity, dark matter, or cosmic expansion? The turning point was not just a single discovery, but a convergence. It was the moment when our instruments reached deep enough to see the universe as it was, and our models began to crack under the weight of that vision. We saw too much, too fast, too soon. We found acceleration where we expected deceleration. We found complexity where we predicted simplicity. We found missing mass, and then missing energy, and then, somehow, a missing framework. Cosmology was no longer about refining a nearly complete theory. It was about confronting the fact that our theory was incomplete at the core. The search for dark energy became one of the most urgent quests in physics. Is it a cosmological constant, as Einstein once proposed and then doubted? Is it vacuum energy, a byproduct of quantum fluctuations? If so, why is its value so small, when quantum field theory predicts it should be enormously large? This is the cosmological constant problem, worst theoretical prediction in the history of physics, off by a factor of 10 circumflex 120. Is dark energy a dynamic field that changes over time, what some call quintessence? Is it a sign that general relativity breaks down on cosmic scales? Or is it a shadow of something more radical, new dimensions, new particles, new laws? To answer these questions, new tools are being built. The Euclid Space Telescope, launched by the ESA and the Vera C. Rubin Observatory, under construction in Chile, are designed to map the large-scale structure of the universe in exquisite detail. They will trace how galaxies cluster, how voids evolve, how space stretches over time. They will test whether dark energy is constant or evolving, uniform or clumped. At the same time, gravitational wave detectors like LIGO and Virgo are opening a new window on the universe synod through light, but through ripples in space-time itself. These waves carry information about the most violent events in the cosmos: black hole mergers, neutron star collisions, the echoes of inflation. They allow us to hear the universe as well as see it. Each of these advancements marks another step past the turning point. We are no longer content to observe. We want to understand. But understanding now requires more than better data. It requires new physics. The standard model of particle physics, though powerful, does not explain dark matter, dark energy, or the mechanism of inflation. General relativity, though elegant, fails at singularities and quantum scales. We stand, once again, at the edge of what we know, facing a frontier not of distance, but of comprehension. And yet, the very fact that we have reached this point is astonishing. A species of primates, evolved on a small rock around a medium star, has built tools that can see the beginning of time. We have measured the age of the universe, the shape of space, the nature of its contents. We have mapped the sky with such precision that we can detect subtle anomalies in the temperature of photons from 14 billion years ago. We have found planets around distant stars, moons with oceans beneath their crusts, galaxies colliding in cosmic ballets. But with each answer, the questions multiply. The universe is not a riddle to be solved once, but a symphony unfolding endlessly. Dark energy is not a final revelation, it is a doorway, a clue, a crack in the frame through which new light can enter. We now suspect that our universe is not only expanding, but accelerating into a future where galaxies will vanish from view, where time itself may stretch beyond recognition. We live in a narrow window of visibility, where the light of distant galaxies still reaches us. One day, even that light will fade. The cosmos will grow quiet, and our observable horizon will shrink to a lonely island of stars. And so the turning point is not only scientific, it is temporal. We are alive in the golden age of cosmologia, brief moment when we can see enough to ask and understand enough to be humbled. Could it be that the problem isn't the universe, but the way we're trying to understand it? For centuries, we've studied the cosmos with increasingly refined instruments, sharper equations, and ever more ambitious models. We've broken the universe into particles and forces, mapped its earliest light, and even simulated its evolution on supercomputers. And yet, something continues to elude us. The deeper we look, the more the edges of our understanding blur. Perhaps it's not just that we're missing information, but that we're asking the wrong questions. Or worse, that we're trapped in the wrong framework entirely. This idea that a change in perspective could be the key to resolving the deepest mysteries of the universe is not new. In fact, some of the most revolutionary moments in science have come not from new data, but from new ways of seeing. One of the most radical perspective shifts in modern physics is the holographic principle. This theory proposes that all the information contained within a volume of space can be described by information encoded on the boundary of that space, like a hologram, where a three-dimensional image is encoded on a two-dimensional surface. The idea emerged from the study of black hole thermodynamics, particularly from efforts to resolve the black hole information paradox. In the 1970s, physicist Jacob Bekenstein showed that the entropy of a black hole's information content was proportional not to its volume, but to the surface area of its event horizon. This was deeply counterintuitive. In every other context, information scales with volume, but black holes seem to follow a different rule. Stephen Hawking's discovery that black holes emit radiation complicated things further. If black holes can evaporate over time, then what happens to the information about the matter that fell in? Does it disappear forever? That would violate one of the most sacred principles of quantum mechanics. That information cannot be destroyed. The holographic principle, introduced by Gerard Hooft and later elaborated by Leonard Susskind, offered a possible resolution. Perhaps everything that happens inside the black hole is actually encoded on its surface. More broadly, perhaps our entire universe can be described by information written on a distant boundary like a cosmic hologram. This isn't just a metaphor. In certain formulations of string theory, such as the ADS, CFT correspondence developed by Juan Maldacena, this principle is precise and mathematical. A gravity theory in a three-dimensional space can be equivalent to a quantum field theory on a two-dimensional boundary. The implications of this are staggering. If the universe is a hologram, then space itself may be emergent, not fundamental. That is, space might not be a basic ingredient of reality, but a macroscopic phenomenon that arises from more fundamental, non-spatial processes. This is a profound shift in perspective. It means that asking about the edge of the universe might be like asking about the edge of a movie scene. The edge doesn't exist within the scene, it's a projection from elsewhere. In this view, questions about the shape or size of the universe could be ill-posed, like asking how many miles long a dream is. And this is only one of several alternative frameworks being explored. Loop quantum gravity, for instance, suggests that space is not continuous but quantized, like a fabric woven from discrete loops. In this theory, space and time themselves are granular at the smallest scales. The Big Bang may not have been a beginning, but a bounce, a transition from a previous contracting universe. These ideas offer potential ways to resolve singularities and unify quantum mechanics with general relativity. They also suggest that time, like space, may be emergent something that arises only under specific conditions. If that's true, then our very notion of causality could be an approximation, valid only within certain regimes. Changing perspectives also reshapes how we interpret observations. For decades, we assumed that dark matter and dark energy were substances, things that exist and exert force. But what if they are effects of deeper geometric or informational principles? What if the apparent acceleration of the universe is a sign that we are misunderstanding gravity at large scales? Modified gravity theories, such as MOND, modified Newtonian dynamics, and TVES, tensor vector scalar gravity, attempt to explain galactic rotation curves without invoking invisible matter. While these theories face challenges, they underscore the broader point. Our interpretation of data is only as good as the frameworks we use to explain it. Even quantum mechanics, long seen as the theory of the very smallest, increasingly recognized as essential for understanding the cosmos as a whole. Quantum fluctuations in the early universe seeded the structure we see today. Galaxies, clusters, voids. The inflationary period, if it occurred, magnified tiny quantum variations into the large-scale patterns observed in the cosmic microwave background. In this way, the distribution of galaxies across billions of light years is, in a sense, a fossil record of quantum randomness. But there's more. Quantum entanglements, considered a peculiar feature of subatomic particles, may play a fundamental role in the fabric of space-time itself. Some physicists now propose that space-time is woven from entanglement, that the connectivity of space arises from the informational links between quantum states. This idea represents another profound shift. It means that geometry might not be the stage upon which reality plays out, but a consequence of deeper quantum informational relationships. If true, it could explain why general relativity and quantum mechanics have proven so hard to reconcile. They may not be two separate theories, but two approximations of a deeper emergent reality. Entanglement, long relegated to the weird corners of quantum physics, might be the foundation of everything. The boundary between quantum and classical, micro and macro, individual and cosmic, begins to dissolve. Changing perspectives also challenges the cultural and psychological narratives we build around science. For centuries, we have told ourselves that science progresses in a straight line, that knowledge accumulates, and theories improve through refinement. But many of the greatest revolutions in science have come not from refinement, but from rethinking. Copernicus didn't add a correction to the Ptolemaic model, he replaced Earth's central position with the Sun's. Einstein didn't tweak Newton's law, introduced a new conception of space and time. Quantum theory didn't extend classical mechanics, it overturned its basic assumptions. Today, we may be standing on the edge of another such revolution, not because we lack data, but because we may need to reframe what the data means. The role of technology in this process cannot be overstated. Telescopes like Hubble, Planck, and James Webb are not just tools, they are lenses through which we view the universe. And what we see depends on how we look. New instruments don't just provide sharper images, they force new interpretations. Gravitational wave detectors allow us to hear the universe, not just see it. Neutrino observatories detect ghost-like particles that pass through matter, offering clues about processes deep within stars and supernovae. Quantum computers and artificial intelligence are beginning to assist in the analysis of cosmological data, detecting patterns that humans may miss. As our tools evolve, so too do our theories, but only if we are willing to let go of outdated assumptions. There's a danger, of course, in shifting perspectives too freely. Not every radical idea is correct. Not every challenge to orthodoxy is valid. But there's also a danger in clinging too tightly to frameworks that no longer serve us. Science is not a doctrine, it is a method. A method that thrives on doubt, on curiosity, on the courage to ask whether the path we're on is the right one. The current tension in cosmology between what we observe and what we expect is not a crisis. It's a crucible, a chance to forge new ideas in the fire of contradiction. The deeper we delve, the more we realize that reality may be far stranger than our current concepts allow. Space might not be a container, but a computation. Time might not flow, but emerge. The universe might not be a thing in itself, but a process, an experience, a story told through interactions and observations. And if this is true, then we are not just observers of the cosmos, we're participants in its unfolding. Our questions shape its answers. Our frameworks shape its form. This doesn't mean that truth is relative or that anything goes, but it does mean that the universe is not obligated to conform to our intuitions. And when it doesn't, it invites us to grow, to stretch our minds, our mathematics, our metaphors, to consider that maybe, just maybe, we're looking at the whole thing sideways. The shift in perspective is not about giving up on science. It's about honoring science as a living process, one that changes as we do. It's about remembering that every great breakthrough began with a question that others thought was foolish. So what if the universe is a hologram? What if space and time are illusions? What if we are looking for edges in a dimensionless landscape, chasing boundaries that don't exist? These may seem like abstract musings, but they are also the frontier. They are the questions that lead us out of the cave of familiar shadows and into the light of new understanding. They ask us not just to see more, but to see differently. And that may be the greatest shift of all. It began as a whisper, just a subtle anomaly, a deviation in the data that no one could quite explain, a strange asymmetry in the cosmic microwave background, an unexpected clustering of galaxies, a pattern in quantum fluctuations that didn't match the models. At first, these were dismissed as noise, as statistical flukes, as artifacts of measurement. But they returned again and again until they could no longer be ignored. Cosmology, once a field anchored in broad consensus, began to tremble. Something was wrong, or perhaps something was right, but we had been looking through the wrong lens all along. And as the cracks deepened in our standard models, an unexpected twist emerged, revealing a cosmos far stranger, far less singular, and far more layered than anyone had imagined. For decades, the WCDM model, the standard model of cosmology, had reigned supreme. It explained the evolution of the universe from the Big Bang to the present day, incorporating dark energy, lambda, cold dark matter, CDM, and the observable matter and radiation we see around us. It matched observations beautifully. The cosmic microwave background, CMB, measurements from WMAP and Planck supported its predictions. Supernova data confirmed the accelerating expansion. Large-scale structure surveys revealed the filamentary web of galaxies it described. And yet, it was never a complete theory. It required invisible ingredients, dark matter and dark energy, that had never been directly observed. It treated inflation, the early exponential expansion of the universe, as a precondition but not a fully understood mechanism. And it offered no insight into why the universe seemed so finely tuned for life, so balanced on the edge between eternal expansion and gravitational collapse. Then came the twist. The James Webb Space Telescope, peering deeper into time than ever before, discovered mature, massive galaxies existing just a few 100 million years after the Big Bang, far earlier than our models allowed. These galaxies were too large, too complex, too old-looking for such a young universe. They appeared to form and organize themselves in ways our simulations could not replicate. Simultaneously, surveys of cosmic expansion revealed a growing discrepancy between local and distant measurements of the Hubble constant, the rate at which the universe is expanding. This so-called Hubble tension suggested that either new physics was at play or our interpretations were flawed. The fabric of our cosmological narrative, so elegant and satisfying, was beginning to fray. And into that tension stepped the multiverse. Long relegated to the realm of philosophical speculation and science fiction, multiverse theories began to gain traction not because we wanted them to be true, but because our current theories seemed to require them. Eternal inflation, the idea that inflation didn't stop everywhere at once, but continued in different regions of space, predicted the existence of multiple pocket universes, each with its own physical constants, its own laws, its own histories. In some, gravity might be stronger or weaker. In others, stars might never form, or black holes might dominate. Our universe, in this view, is just one bubble in a frothing sea of reality, and we exist here, not because this universe is special, but because it permits observers to exist at all. This was the anthropic turn. The idea that our universe is not fine-tuned for life because of a grand design, but because we are here to notice it, If life could only arise in rare types of universes, then of course we would find ourselves in one of those. It's not surprising we're a statistical inevitability. This perspective shattered the illusion of cosmic uniqueness. It replaced certainty with probability, law with landscape, universality with contingency. It was a humbling realization. The laws we observe may not be universal at all. They may be local features of our own pocket of the multiverse, not reflections of deeper truth, but random conditions written in the chaos of inflation. Not everyone accepted this willingly. The multiverse seemed untestable. It violated the traditional criteria of falsifiability. How do you study what lies beyond the observable universe? How do you prove or disprove the existence of other realities you can never touch, see, or measure? But defenders pointed out that science has always moved forward by expanding its boundaries. Once, atoms were theoretical. So were black holes, gravitational waves, and the Higgs boson. What matters is not current observability, but the potential for evidence. And some claimed that evidence might exist not in direct observation, but in subtle imprints. Collisions between bubble universes could leave circular scars in the CMB. Patterns of anisotropy might reveal deeper structure. The very distribution of constants, masses, and interactions in our universe might hint at an underlying landscape. And still, the twist grew stranger. As quantum physics advanced, another idea began to emerge from the shadows. The simulation hypothesis. What if the universe is not a physical entity at all, but a computational one? What if we are not embedded in matter, but in code? This notion, popularized by philosopher Nick Bostrom, proposes that if advanced civilizations gain the ability to simulate entire universes with conscious observers, and if they have the motivation to do so, then statistically, it is more likely that we are in one of those simulations than in the base reality. The universe's quantized structure, its adherence to probabilistic laws, its digital seeming limits, like the Planck length or the speed of light, all became reinterpreted as possible signs of an underlying computational substrate. To many, this was absurd. To others, it was a revelation. If the universe is a simulation, then questions of origin and purpose take on new meaning. The Big Bang could be the boot-up moment. Dark energy could be an algorithmic parameter. Quantum indeterminacy might reflect limits in computational precision or design. And suddenly, the idea of an edge to the universe made sense again, not as a spatial border, but as a programmed constraint, a boundary condition defined by the system's architecture. In this view, the multiverse becomes not a sea of physical bubbles, but a library of simulated realities, some fantastical, others indistinguishable from our own. The fundamental nature of reality itself becomes an open question. And yet, whether we inhabit a simulation or a self-contained quantum cosmos, a deeper realization begins to dawn. Our understanding of the universe is no longer progressing linearly, but fractally expanding outward into multiple competing possibilities. The search for truth has become a map of options, each with its own internal logic, each challenging the others, and each exposing the assumptions baked into the way we frame questions. We are learning not just about the universe, but about the limits of human cognition. We are confronting a truth that transcends equations, that our place in the cosmos is not fixed, not central, not guaranteed. We are neither the masters of creation nor its inevitable outcome. We are witnesses, perhaps fleeting, perhaps rare, but undeniably real, tracing meaning across a canvas we may never fully see. And in this tension between discovery and mystery, between knowledge and humility lies the true twist. The deeper we go, the more we find that reality resists simplification, that the universe may not offer a single explanation, but a spectrum of interpretations, that the answers we seek may be tangled with the questions we ask, and that we, the observers, are not outside the experiment, but part of it. Our instruments shape what we measure. Our models shape what we see. Our minds, evolved on one small planet, around one ordinary star, are trying to grasp a reality that may have no end, no edge, and no final answer. So, what does this mean for us? It means that the cosmos is not a riddle to be solved once, but a mystery to be lived with. It means that the unexpected is not an aberration, but a feature. That twists in the story are signs that we are moving forward, not losing our way. It means that our place in the universe is not defined by certainty, but by inquiry, not by dominance, but by participation. We are not insignificant. We are the part of the universe that asks questions, that imagines alternatives, that dares to wonder whether everything we know might be wrong and finds, in that doubt, the beginning of deeper understanding. In the end, the unexpected twist is not just about dark energy, or multiverses, or simulations. It is about perspective. It is about learning to see the familiar as strange again, to embrace the possibility that the edge we seek is not out there, but within our own models, our own assumptions, our own limitations. The cosmos remains silent. It does not explain itself, but in that silence, we find space for imagination, for science, for awe, and perhaps that is the most profound twist of all, that the universe, in revealing its strangeness, teaches us not only what it is but who we are. Despite the breathtaking discoveries of the last century, the expansion of the universe, the existence of dark matter and dark energy, the Big Bang, the cosmic microwave background, exoplanets, gravitational waves, we find ourselves today not standing atop a mountain of complete understanding, but peering over the edge of a deeper mystery. For every veil we've lifted, a new one appears. Our tools have brought the cosmos closer, but they've also revealed how much lies beyond our current reach. The next great chapter in cosmology and astrophysics will not be about refining what we already know, but confronting the unknown head-on. And doing so will require overcoming challenges that are as vast, subtle, and complex as the universe itself. The first and most pressing challenge is technological. For all their brilliance, today's observational tools are constrained by fundamental limitations. The James Webb Space Telescope has given us unprecedented access to the early universe, revealing galaxies we never expected to find so early after the Big Bang. But even JWST cannot see everything. It cannot penetrate the cosmic curtain before the surface of last, scattering the point roughly 380,000 years after the Big Bang, when the universe became transparent to radiation. The light from before that time is forever hidden from traditional telescopes. To access it, we need to move beyond light altogether. We need to study gravitational waves, neutrinos, and other messengers that can pass through the opaque early universe, bringing us closer to the beginning than photons ever could. But even here, we face obstacles. Gravitational waves, while revolutionary, are incredibly faint. Our current detectors LIGO, Virgo, and CAGRA only pick up the most cataclysmic events, black hole mergers, neutron-star collisions. They are deaf to the subtler murmurs of the universe's first moments. To detect the primordial gravitational wave background, we need new types of observatories. Space-based detectors like the Laser Interferometer Space Antenna, LISA, which will be sensitive to lower frequency waves produced by cosmic inflation, cosmic strings, or phase transitions in the early universe. These missions are already being designed, but they are years, sometimes decades from launch. And once launched, they will require unprecedented precision, coordination, and interpretive clarity. The signals will be weak, the noise will be high, but the stakes are enormous. Beyond gravitational waves, the field of neutrino astronomy is still in its infancy. Neutrinos are ghostly particles that rarely interact with matter, making them difficult to detect but invaluable as messengers from deep inside stars, supernovae, and potentially the Big Bang itself. Instruments like IceCube at the South Pole have begun to capture high-energy neutrinos from deep space. But detecting the cosmic neutrino background, the relic neutrinos from the Big Bang, remains out of reach. Doing so would be a monumental breakthrough, confirming long-standing predictions of the standard model of cosmology and giving us a new probe into the structure of the early universe. But it will require detectors far more sensitive than any we currently possess, detectors that may need to be built in space or deep underground, shielded from all other forms of radiation. Another major hurdle is cosmic variance. No matter how advanced our telescopes become, we are ultimately limited by our position in the universe. We can only see one observable patch of sphere, about 93 billion light-years across. That's vast, yes, but it's still just one realization of what the universe might be. If the universe is infinite, or contains wildly different regions, we may never know. We cannot step outside our cosmic horizon to compare notes with another vantage point. This imposes a hard boundary on what we can test statistically. It also complicates efforts to measure things like the true curvature of space, the topology of the universe, or the distribution of rare phenomena. Compounding this is the fact that many of our most pressing cosmological questions have become questions of precision. How fast is the universe expanding? What is the exact mass of the neutrino? What is the equation of state for dark energy? Each of these questions has answers that lie in the decimal points of data, in the subtle shifts of curves, in the small deviations from theoretical expectations. Extracting those answers requires not only better instruments, but better modeling of astrophysical foregrounds, all the messy, complicated structures that lie between us and the signal we want to measure. Galaxies, gas clouds, dust, magnetic fields, all of these contaminate our observations. Separating signal from noise is becoming the central challenge of cosmological data analysis. The dark matter problem remains a towering enigma. For all the gravitational evidence of its existence in galaxy rotation curves, gravitational lensing, the cosmic web, we still have no direct detection of dark matter particles. Experiments like Xenaut, Lux Zeppelin, and Super-CDMS are pushing the limits of sensitivity, seeking elusive interactions between dark matter and ordinary matter. So far, they have come up empty. This forces us to ask, what if dark matter is not a weakly interacting massive particle, WIMP? What if it's a different class of entity altogether, an axion, a sterile neutrino, or something even more exotic, like primordial black holes or dark sector forces? Each possibility demands a different kind of experiment, a different set of assumptions, and each null result tightens the noose around existing theories, pushing physicists to think outside the standard model. Dark energy, too, remains opaque. Is it truly constant, as Einstein's cosmological constant suggests? Or is it dynamic, changing over time and space, like a field? To answer this, scientists are designing missions like the Nancy Grace Roman Space Telescope, formerly WFIRST, Euclid, and DESI, Dark Energy Spectroscopic Instrument, each of which will map the distribution of galaxies and the geometry of the universe with unprecedented detail. They will measure baryon acoustic oscillations, weak lensing, and redshift space distortions to constrain the behavior of dark energy. But interpreting their results will require new models that go beyond WCDM models, that can incorporate modified gravity, coupled dark energy, or even violations of fundamental symmetries. One of the most intriguing frontiers is the intersection of cosmology and quantum mechanics. Increasingly, researchers believe that the key to understanding the universe lies not in space-time itself, but in the quantum informational relationships that underlie it. Ideas like the holographic principle, quantum gravity, and emergent space-time point toward a future in which geometry is not fundamental, but derived. If this is true, then many of the edges we seek, temporal, spatial, causal, may be illusions, artifacts of a deeper, non-local reality. Testing these ideas, however, is extraordinarily difficult. They require new formulations of physics, new interpretations of quantum theory, and potentially new mathematics. And yet, the promise is too great to ignore. If space-time is emergent, then so too are mass, energy, and the laws that govern them. The entire universe may be the byproduct of deeper, invisible rules that we are only beginning to glimpse. Another major challenge is philosophical. How do we maintain scientific rigor in a domain where many ideas are currently untestable? The multiverse, the simulation hypothesis, the landscape of string theory, these concepts stretch the traditional boundaries of science. They invite speculation, imagination, even metaphysics, but they also risk drifting away from falsifiability, the cornerstone of the scientific method. The challenge for future scientists will be to balance openness with discipline, to explore boldly, but not recklessly, to recognize that not all beautiful ideas are true, and not all true ideas are beautiful. This raises questions about how science itself is organized. As the frontiers of knowledge grow more complex, collaboration becomes essential. No single person can master all the disciplines required to understand the early universe, quantum gravity, and high-energy particle physics. Interdisciplinary teams combining expertise in theory, Observation, computation, and instrumentation will be the norm. So too will international partnerships. Telescopes, detectors, and space missions are expensive, and their scale often exceeds the capacity of any one nation. Scientific diplomacy, shared data, shared goals, shared responsibility will be as vital as technical innovation. Education, too, must evolve. The next generation of cosmologists will need to be fluent not only in general relativity and quantum mechanics, but in machine learning, information theory, data science, and philosophy of science. They will need to navigate an increasingly hybrid intellectual landscape, where the lines between physics, computation, and philosophy blur. They will need to question assumptions that today seem unshakable, and they will need to cultivate humility, patience, and intellectual courage. Despite all these challenges, the outlook is bright. The very fact that we face so many unknowns is not a sign of failure, it is a sign of vitality. Science is healthiest when it is most uncertain, when it has room to grow, when its old answers no longer suffice, and new questions demand new ways of thinking. We are not at the end of cosmology. We are at the beginning of a new era, one in which technology, theory, and imagination converge to push back the boundaries of the possible. As the 21st century surges forward, the great confrontation at the heart of physics intensifies not with weapons or armies, but with equations, observations, paradoxes, and imagination. The search for the edge of the universe, the ultimate laws of nature, and the unification of the forces that govern existence has brought science to the threshold of something extraordinary. For over a century, physics has been guided by two towering achievements: Einstein's general theory of relativity, which describes gravity and the large-scale structure of the cosmos, and quantum mechanics, which governs the behavior of particles at the smallest scales. Each theory works with stunning accuracy in its own domain, but together they refuse to coexist. The confrontation between them has become the central drama of modern cosmology. It is here at this intersection of the vast and the infinitesimal that the latest generation of theories now clash. At stake is not just the understanding of black holes or the behavior of space-time, but the nature of reality itself. On one side are the advocates of string theory, who argue that the particles and forces we observe are the vibrations of tiny, one-dimensional strings existing in higher dimensional space. String theory promises unification. It can include gravity. It can, in principle, accommodate all known particles and interactions. It introduces the possibility of extra dimensions, hidden from view, curled up at scales too small to detect. And in certain formulations, string theory gives rise to the holographic principle. The idea that the three-dimensional universe is a projection from a two-dimensional surface, an echo of quantum information encoded on a cosmic boundary. String theory's strengths lie in its mathematical beauty and its ability to describe black holes, dualities, and other exotic features of space-time. Its critics, however, point out that it has yet to make testable predictions. Its landscape of solutions is vast, possibly containing 10 circumflex 500 different possible universes. This has led to the controversial notion of the multiverse, where every possible set of physical laws is realized somewhere. Some see this as the ultimate explanation of the fine-tuned parameters of our universe. Others see it as an abandonment of predictive science. Facing string theory across the conceptual divide is loop quantum gravity, LQG, a radically different approach. Instead of embedding particles in strings in space in extra dimensions, LQG proposes that space itself is quantized, built from discrete loops that form a network of relations. In this view, space and time are not continuous, but granular. The Big Bang is not a beginning, but a bounce, preceded by a contracting phase. LQG excels at addressing the singularities that plague general relativity, such as those at the centers of black holes and at the origin of the universe. It maintains background independence, as space-time is not a fixed stage, but something that emerges from the relationships between quantum states. Yet LQG has its own challenges. It lacks a straightforward way to incorporate the standard model of particle physics. It has fewer connections to string theory's powerful dualities. Its predictions are subtle and difficult to test. Beyond these two giants, a host of other contenders and conceptual revolutions are emerging. Causal set theory, non-commutative geometry, asymptotic safety, and emergent gravity models all attempt to bridge the chasm between quantum mechanics and general relativity. Some suggest that gravity is not fundamental at all, but emergenta collective behavior of underlying quantum information. Others propose that time itself is not real, but a product of thermodynamic or entropic evolution. These are not fringe ideas. They are being explored at the highest levels of theoretical physics by researchers who recognize that the path forward may not lie in refining old ideas, but in transcending them. And yet, despite their differences, all these theories circle around a central question: will we ever find the true boundary? Not just the edge of the observable universe, but the fundamental limit of knowledge, the final theory. The one framework that explains everything: why the universe exists, why it has the laws it does, why we are here to ask. Some physicists remain optimistic. They believe that we are close to a breakthrough, that the unification of physics is imminent, awaiting only the right insight or the right experiment. Others are more cautious. They point to Gödel's incompleteness theorems, which show that no consistent system can prove all truths about itself. They warn that the universe may be more complex than our minds can fully comprehend, that the theory of everything may not be a single equation, but an evolving story that reflects our ever-changing understanding. In parallel with these theoretical confrontations, observational cosmology continues to press outward, mapping the distribution of galaxies, tracing the influence of dark energy, and seeking the fingerprints of inflation. The James Webb Space Telescope, the Euclid mission, the Nancy Grace Roman Space Telescope, the Vera Rubin Observatorial are designed not only to observe, but to challenge theory, to test whether gravity behaves as expected on cosmic scales, to see whether the dark sector dark matter and dark energize truly as we imagine, or something else entirely. These missions aim to push past the horizon of current understanding, to provide the empirical grounding for the next revolution. Yet the debate about the universe's boundary persists not only as a technical question, but as a philosophical one. What does it mean to seek an edge in a possibly infinite universe? Is the edge a physical frontier, a conceptual construct, or an illusion? If the universe is truly infinite, then the notion of boundary dissolves. If it is finite but unbounded, like the surface of a sphere, then the edge is nowhere and everywhere. If it is a simulation or a projection, as some versions of the holographic principle suggest, then the edge may exist in a higher dimension, inaccessible to us. And if space and time themselves are emergent, then the edge may not be spatial at all, but informational, quantum, or relational. These possibilities don't just reshape physics, they reshape our understanding of meaning, identity, and place. For centuries, humans sought to define their position in the cosmos first as the center of the universe, then as a planet among many, then as one galaxy among billions. Now we confront a deeper question. Is there a final answer to where we are, or does the question itself dissolve as we approach it? Are we nearing the culmination of physics, or only its next transformation? Unification remains the dream, the holy grail of modern physics. The Standard Model, for all its success, does not include gravity. General relativity, for all its elegance, does not quantize. The great goal is a theory that includes both a quantum gravity that reduces to Einstein's theory on large scales, and to quantum field theory on small ones. But the road is steep. We may need new mathematics, new symmetries, new principles of reality. The path forward may not lie in extrapolating from what we know, but in letting go of what we assume. And here lies the challenge and the promise of the future of cosmology. We are entering an era of synthesis where theory and observation must work together more tightly than ever before, and where interdisciplinary thinking becomes essential. Information theory, quantum computation, condensed matter physics, philosophy, and cosmology are beginning to converge. The very nature of inquiry is changing. We are no longer just looking outward. We are looking inward into the nature of thought, of measurement, of existence, into the very tools we use to ask questions. The final confrontation is not only between theories, it is between us and the cosmos, between our desire for certainty and the universe's infinite ambiguity, between our dreams of unification and the reality of complexity. And yet, in this confrontation, there is beauty, there is progress, there is awe. For all our limitations, we have seen the afterglow of creation. We have traced the invisible threads of gravity and light. We have glimpsed the possibility of other universes, other laws, other ways of being. We have begun to see that the boundary may not be a wall, but a mirror that reflects not just the universe, but our evolving understanding of it. The future of cosmology lies not in conquering the unknown, but in learning to dwell within it. To live not with final answers, but with ever better questions. To navigate the edge not as a limit, but as a horizon. Will we ever find the true boundary? Perhaps not, but we will keep searching. Because in that searching, the equations, the observations, the debates, the dreams, we find what makes us human. We find meaning. And we find, once again, that the edge of the universe is also the beginning of ourselves. In the cold, silent vastness of space, there is no sound, no signposts, no answers written in the stars. And yet, for as long as humans have existed, we have looked up, not just with our eyes, but with our hearts. The night sky has always stirred something in us, something ancient and unnameable. Before we had telescopes or equations, we had wonder. Before we mapped galaxies, we mapped constellations. Before we measured redshift, we whispered stories into the dark. And still today, after centuries of discovery, after uncovering so many truths about the structure and evolution of the cosmos, that primal sense of awe remains. Because behind every photon we catch from deep space, behind every cosmic model, behind every instrument and mission and simulation, lies a moral truth. That to explore the unknown is to reaffirm our humanity. The universe, indifferent though it may be, calls us to become more than we are. Cosmic exploration is not merely the pursuit of data. It is a moral act, a declaration that curiosity matters, that the unknown is worth facing, that truth, however elusive, is worth seeking. In a world often defined by division, distraction, and despair, Real Science offers a different kind of story. A quiet, stubborn story. One that says the universe is not a riddle meant to be solved once, but a journey meant to be walked together. One that says our species, fragile though it is, has chosen to use its brief time not only to survive, but to ask deeper questions about where we come from, what we are made of, and where we are going. Curiosity is not a luxury. It is a necessity. It is the engine of all progress. Without curiosity, there is no science, no art, no philosophy. Without the willingness to step into uncertainty, we remain trapped in the known. And the known, over time, becomes a prison. Every great scientific breakthrough began with a question that seemed naive, pointless, or even dangerous. What lies beyond the stars? What is the nature of time? Why does gravity pull? What happens if you travel at the speed of light? These are not practical questions, not immediately useful, but they are the questions that gave rise to relativity, quantum mechanics, cosmology, and the very technologies that now define our civilization. Every innovation, every leap begins as an act of faith in the value of asking. But curiosity alone is not enough. It must be tempered by humility, by the recognition that the universe does not owe us understanding, that every answer opens 10 more questions, that the deeper we look, the more we see that reality is not obligated to fit our expectations. Science, at its best, walks a line between confidence and wonder. It builds theories, but accepts when they fail. It makes predictions, but learns from the unexpected. It embraces the mystery not as a threat, but as a guide. And this too is a moral lesson. That wisdom is not found in certainty, but in balance, in the willingness to learn, to revise, to grow. Cosmic exploration teaches us, again and again, that we are not the center of the universe, and yet we matter. We are not insignificant because we are small. We are significant because we are aware. The universe may be vast, silent, and indifferent, but we are not. We are the part of the universe that notices, that asks, that dreams. That builds observatories on mountaintops and launches telescopes beyond Earth's atmosphere, not for conquest or profit, but for understanding. The most powerful moral takeaway from science is this: we are capable of transcending ourselves. We can choose meaning even in the face of the void. This lesson is especially important now, in a world facing existential threats from climate change, war, and inequality, to the accelerating pace of artificial intelligence and ecological collapse. In the shadow of these crises, it may seem indulgent to care about galaxies billions of light years away. But the opposite is true. The act of looking outward is also an act of looking inward. The same skills that let us study black holes' collaboration, patience, rigor, imagination are the same skills we need to solve problems here on Earth. The same humility that lets us accept uncertainty in cosmology is the humility we need in politics, in ethics, in daily life. And the same curiosity that drives space exploration can drive us to care about each other, about the planet, about the future. There is another moral lesson, too often overlooked. In studying the cosmos, we learn not only about stars and gravity, but about time, about patience. The light we see from distant galaxies left its source billions of years ago, long before Earth even formed. We are witnessing history written in light, unfolding across eons. This forces us to expand our sense of time, to think not in years or decades, but in cosmic ages. And this shift in perspective can transform how we see ourselves. We become part of a much larger story. Our lives, our joys and sorrows, our civilizations, they are chapters, not conclusions. And that realization can be both humbling and empowering. It reminds us that the future is not fixed, that what we do now matters, that even small actions can ripple through time in ways we cannot predict. Cosmic exploration also teaches us about unity. From orbit, there are no borders, no flags, just one fragile planet wrapped in a thin blue atmosphere. The overview effect experienced by many astronauts is a profound psychological shift that occurs when seeing Earth from space. It dissolves divisions. It instills a sense of shared responsibility. And it can happen from the ground, to from looking through a telescope, or watching a documentary, or simply gazing at the stars and realizing that we are all here together on one tiny world in a vast and ancient universe. This awareness is not sentimental, it is scientific, and it is moral. It says, we are each small, but together, we are part of something magnificent. But even as we celebrate the power of knowledge, we must remember to honor the mystery. Not every question will have an answer. Not every theory will be complete. And that's okay. Mystery is not the absence of understanding. It is the presence of possibility. It is the space where new ideas are born, where imagination thrives, where wonder lives. The best scientists are not those who claim to know everything, but those who remain open to being wrong, open to surprise, open to the unknown. This openness is a kind of moral stance, a willingness to live with uncertainty, to find beauty in the incomplete, to let go of control and embrace curiosity. So what is the deeper meaning of exploring the unknown? It is the cultivation of character. It is the practice of becoming better observers, not just of the universe, but of ourselves. It is a way of expanding the mind and the heart at the same time. When we ask what lies beyond the edge of the universe, we are also asking what lies beyond the edges of our own understanding. When we trace the life cycles of stars, we are also tracing the patterns of life, death, and rebirth in our own experience. When we ponder whether time began at the Big Bang, we are also pondering the value of each moment we are given. These are not separate pursuits. They are deeply connected. Science is not cold. It is not detached. It is one of the most passionate, creative, and courageous things humans do. It takes courage to stare into the abyss of infinity and still try to draw meaning from it. It takes creativity to build tools that can catch the faint whispers of creation. It takes humility to know that we may never have all the answers, but we can still ask better questions. And it takes love for truth, for beauty, for possibility. As we move into the future of cosmology with new missions, new theories, and new uncertainties, we must carry these moral lessons with us. We must teach them, share them, live them, because the universe will not change because we observe it, but we will. And that change the growth of curiosity, humility, unity, and wondrous, the true value of exploration. Not just the knowledge we gain, but the kind of beings we become in the process. We are the children of stardust, born in a universe vast beyond comprehension. We are brief, but luminous, temporary, but capable of reaching across time with our questions and our courage. We will not find all the answers, but we will keep searching, not because we expect to solve everything, but because searching is what makes us human. Because in that search, we become more than mere biology. We become seekers, storytellers, explorers of both the cosmos and the soul. So let us look up, not just with our eyes, but with our whole selves. Let us teach our children to wonder. Let us build a future not only of knowledge, but of meaning. Let us remember that the stars are not just lights in the sky. They are reminders of who we are and who we might become. In the darkness between galaxies, in the silence of deep time, in the unfolding questions that shape our understanding, we find not despair, but hope, not emptiness, but invitation. And in that invitation lies the deepest moral takeaway of all, that the universe is not just something we observe, it is something we are part of. And our journey through it, if we choose to walk it with courage and curiosity, can lead us not only to the stars, but to a more luminous vision of what it means to be human. There comes a point in every great journey when one must choose between closure and continuation, between tying the final knot or leaving the thread hanging, between declaring the last word or opening the floor for new voices. In cosmology, in science, in the search for the structure and meaning of the universe, that moment is now. With the tools of modern physics and astronomy, we've traveled light years in our minds and machines. We've looked backward to the earliest fractions of time and outward across billions of galaxies. We've named forces, charted patterns, and built models that frame the dance of matter and energy. And yet, the deeper we go, the more we find that every answer leads to a corridor of deeper questions. Every discovery is a key that unlocks not a room, but a labyrinth. So, we must ask, should the mystery of the cosmos ever be closed? Or is its enduring value precisely that it stays open? To ask this is to acknowledge something fundamental, that the unknown is not merely a gap in knowledge, but a source of meaning. The universe, with all its vastness and silence, is not a puzzle to be finished and put away, but a canvas always being drawn. There is power in uncertainty. There is beauty in mystery. And in many ways, the greatest moral and intellectual lesson of cosmic exploration has been learning to sit with the unanswered. The universe does not bend to our timelines. It does not offer tidy endings. It unfolds in complexity, in surprise, in strangeness, and in that unfolding, we find not frustration, but inspiration. Throughout the story of science, unanswered questions have always been seeds of progress. Newton's failure to explain the nature of gravity led to Einstein's theory of general relativity. The ultraviolet catastrophe in classical physics led to quantum mechanics. The unification of electricity and magnetism in the 19th century paved the way for the Standard Model, which now itself demands unification with gravity. Cosmology has followed a similar arc, from the Ptolemaic spheres to the Copernican revolution, from static models to expanding ones, from Big Bang simplicity to the complexity of inflation, dark energy, and the multiverse. We've moved from closure to greater openness. The closer we think we are to a final answer, the more the cosmos reminds us that there is no final page, only a widening horizon. And perhaps that is as it should be. If we were to find a single all-encompassing theory of everything, that explained all phenomena, all constants, all boundary, it would be a monumental achievement. But even then, it would not end the story. Because the meaning of that theory, its implications, its connections to consciousness, time, possibility, and being, would themselves open new philosophical and scientific vistas. There would still be questions about why that theory exists, why it is elegant, why it allows life, thought, and self-reflection. The mystery would not end. It would simply evolve. The open-endedness of cosmic mystery is not a flaw. It is a feature. It invites us to continue asking, not with despair, but with wonder. It tells us that science is not a monument, but a movement. That knowledge is not static, but alive. And in that dynamic, ever-expanding conversation, we become more than passive observers. We become creators of meaning. So what are the great takeaways from this journey into the cosmos? First, we've learned that the universe is vastly more complex, beautiful, and surprising than any myth or model ever imagined. It is expanding, accelerating, filled with dark matter and dark inner forms of reality that outweigh the visible, that shape the very structure of space and time, yet remain fundamentally mysterious. We've learned that we live in a universe with no fixed center, no edge we can reach, and possibly no end. A universe that may be infinite or finite but unbounded, one that may be one of many or a unique miracle, one that may be a simulation, a hologram, a computation, or something entirely beyond our language and thought. Second, we've learned that our tools and ideas are always evolving. From Galileo's telescope to Hubble's, from Newtonian gravity to Einsteinian spacetime, from classical particles to quantum field we've built layer upon layer of understanding. But we've also had to revise our assumptions again and again. We've learned to be skeptical, but not cynical, bold, but not arrogant. Science thrives in humility. It progresses by admitting what it does not know, by failing better each time. Third, we've learned that we matter not because we are the center of the universe, but because we are capable of asking questions about it. We are a conscious thread in the tapestry of the cosmos, a species that emerged from stardust and learned to reflect on its origin. That alone is extraordinary. We may be small in size, but we are vast in imagination. We build instruments that capture ancient light, models that simulate galaxies, theories that bridge the micro and the macro. We create stories, languages, and cultures inspired by the stars. Our curiosity gives us dignity. Our questions give us purpose. Fourth, we've learned that science is not the opposite of meaning, it is a pathway into it. The more we explore, the more we realize that knowledge and mystery are not in conflict. They are in balance. Knowledge gives us tools. Mystery gives us direction. Knowledge grounds us. Mystery lifts us. Together, they form a compasso way to navigate not just the external world, but our internal lives. The infinite possibilities of space are not abstract. They are personal. They challenge us to rethink who we are, what we value, and how we live. They remind us that life is fragile, precious, and rare. That the Earth is a single point of warmth in a cold and expanding sea. That our differences of nation, race, religion, ideology are insignificant compared to what we share. One planet, one chance, one brief moment to look up and wonder. Cosmic exploration is a mirror. It shows us what we are made of literally and metaphorically. We are made of hydrogen and carbon, iron and oxygen, born in stars, scattered in supernovae. But we are also made of questions, of dreams, of the desire to reach further. The universe is not just out there. It is in us, in our atoms, in our curiosity, in the fact that we can even conceive of the cosmos at all. So, should we close the story? Should we declare the mystery solved? Should we hope for a final answer that locks the universe into a neat, complete model? Or should we leave it open? The truth is, the story was never meant to close. The cosmos is not a novel, it's an improvisation, a song that unfolds in verses, keys, and rhythms beyond any final chorus. The mystery should remain open because it is what drives us forward, because it keeps science honest, because it honors the vastness of the unknown. Leaving questions unanswered is not a sign of weakness, it is a sign of strength. It takes courage to say, I don't know. It takes even more to say, let's find out. It is in that spirit not of conclusion, but of continuation that the future of cosmology must proceed. We will keep building telescopes, probing quantum gravity, searching for dark matter and dark energy, mapping the cosmic web, simulating the early universe. We will keep asking whether space and time are emergent, whether the universe is one of many, whether the laws of physics are fixed or statistical. We will keep looking not just for answers, but for better ways to ask. And in doing so, we will write the next chapter not of certainty, but of wonder. So, let us embrace the open ending. Let us celebrate the not knowing. Let us teach our children not just what we have learned, but how we learned it through questioning, doubting, imagining, testing. Let us make science not a list of facts, but a culture of curiosity. Let us honor the infinite possibilities of space by cultivating infinite minds, infinite compassion, infinite hope. Because in the end, the universe does not need us. It would go on expanding, collapsing, evolving, even if we were never here. But we need the universe. We need its mystery, its challenge, its beauty. It calls us to grow, to reach, to become. And that is the true story. Not a conclusion, not a solution, but an invitation to wonder forever.